In this third podcast, we're going to do a detailed analysis of insertion sort. I should warn you that the level of detail is very tedious, and we're doing this to show both the mathematical basis for analysis of runtime, but also to show the wrong way to do it. We actually don't want to have to go into much detail, as I'm going to show you in this session. So partly I'm showing you the great tedious detail just so you appreciate what we learn about in part 3, the use of asymptotic growth analysis to characterize the rate at which functions grow. Okay, so let's begin. Question at hand here is, how do we characterize how much time it takes an algorithm to run? So we need to count some kind of operations. So we need to assume that this algorithm is running on some kind of machine, that we can count the basic operations of the machine. Typically we use what is called the random access model. So we need to know what basic operations on these machines to count. Some of the operations that we count will be data manipulation operations, such as those listed here. Doing arithmetic, comparing numbers or other comparable objects, doing logical operations, and so on. Now, each of these operations may take a different amount of time than other ones. Addition is quicker than multiplication, and you can think of many other examples like that. But the point here is that all of these are bounded from above by a constant. We're also going to count other kinds of operations like flow control, branching based on the comparison operations or the logical operations. We might branch, and looping operations. Finally, there's other miscellaneous operations that we might count, including assignment, subscription. It takes some math, some basic arithmetic to figure out where to go into memory when you subscript an array. Following references to objects, setting up function calls requires moving some information around in memory. Now, it's important that the things that we count are bounded by some constant, that we don't include in our operations, essentially operations that solve the problem that we're trying to solve with the algorithm. We would not count a sort command as a primitive operation, because how long it takes to sort something grows as a function of the size of the input. Okay, let's now look at each line of this program and write an expression for the cost to execute each line. Now, we don't know exactly how many steps or how many milliseconds it takes for an operation like assignment or comparison to operate. So we're just going to write in constants. For example, in this line here, we have j equals 2 to a.length. So there's an initial assignment, and then there's a comparison each time, and then it'll branch depending on the result of that comparison. So we don't know what that cost is, but we'll just assign a constant letter, c sub 1 will represent whatever that cost is to execute one pass through those operations. And so we just got to ask, how many times does that happen? Well, we're running from 2 to a.length, so it sounds like if the input size is n, we're doing it n-1 times. But we have to remember that even on the exit of the loop, the operations, some of these operations are carried out to make the test before the exit. So it actually runs up to j being a.length plus 1. So it's actually going to happen n times. So some constant c sub 1 cost aid n times. So we just play the same game here going down. We don't know what one execution of this line takes. We'll just give it a name. This is something we often do in algorithm analysis. If we don't know an actual value, we just give it a name, and then either the term goes away, we never have to know what it is, or so later on we find a way to figure out what it is. So here c2 will be the cost to subscript this array, get that information out of the array, and assign it to the variable key. Now, the outer loop is executed n times, but that's counting the time that we decided to exit the loop and not enter the loop. So everything on the inside here is going to be executed n-1 times. So the cost of this line, c2, executed n-1 times. If you want, we can put a little dot in there for multiplication. Of course, understanding that c2 times this whole expression. Similar thing down here. By the way, your text puts in a cost to 0 for the comment. I don't think the comment is actually going to be in the code once it's compiled, so I thought that was a little silly. So we're going to skip c3. We'll put in c4, whatever the cost of that is. And again, it's paid n-1 times. Now, here things get a little tricky. We know that this while loop will be executed as a whole n-1 times, but we don't know how many times it's going to take to run through each time we encounter the while loop. And in fact, that depends on the data. We can't know just inspecting the code, because it depends on whether each a sub I encountered is greater than or less than or equal to the key, and of course what the key is. So again, if we don't know what something is, we're just going to give it a name. We're going to just use the variable t to represent how many times this whole loop is executed. But that depends on which pass of j we're in. So we're actually going to say t sub j is, and I'm going to write that up here for now because we're going to put it as part of a bigger expression. T sub j represents how many times this outer loop is executed, which depends on the data, and the data changes each pass of j, so that's why it's subscripted by j. And t sub j minus 1, one less time, is how many times the inner loop is executed, for the same reason we had n minus 1 here. T sub j is counting the time that we exit. We're going to write the n minus 1 a little differently. We're going to write it as a summation because we need something to control this j. We need to range this j over all the possible j's from 2 to a.length is the last time it executes. So this first line of the while will be run for values of j equals 2 up to n. And it will cost t sub j. That's just the name we gave to what it costs. These two inner loops, these two inner lines in the loop are both going to have the same expression, but with different constants. So this one here, by the way, was with constant 5. This line costs constant 6, and this line costs constant 7. The number of times that they're executed is the same as this expression up here, except with t sub j minus 1, because we're not counting the time that we exit that loop again. So t sub j minus 1. So that's probably the most complicated part of this analysis, this counting, is realizing, well, we got to give a name to every time we encounter this while loop. It's going to be with different data, so that means the number of times it's executed, it will vary. So let's give it, just to give a name to that, with t subscripted by j to recognize that there's different t's for every time it's encountered. And then because we have to have something control that variable and run it up from 2 to n, instead of writing n minus 1, we just write this summation expression, which obviously runs n minus 1 times because it runs from 2 to n. So essentially this summation is playing the same role as this thing here, but it's also controlling that variable. And then we did the same thing here, except we subtracted 1 because we don't count the time that, the last time that this test fails and we exit. So this expression is going to be multiplied both C6 and C7. Finally, constant 8 times n minus 1 for the cost to execute this last line here. Okay, what we're going to do now is we're going to write this expression all out at the top of the screen, and it's going to be big and complicated, but then we're going to use it, simplify it in certain ways to come up with the best case and worst case of insertion sort. So let's say we write the expression t sub n, meaning the time it takes to do a sort on input of size n, is equal to all these things added up together. So it's equal to C1n plus C2n minus 1 plus C4 n minus 1 plus C5 times the summation j goes from 2 to n, t of j. Okay. I'm going to run off the screen here. It's the n, j equals 2, t sub j plus C6 times the summation j goes from 2 to n, tj minus 1, C6. Same thing for C7. . oops, 1, that's a 1. And we got to add the term for C8. Now, that's a very complicated looking expression, but I want you to notice that you never have to understand these things all in one take. Just looking at that, nobody would understand that. We got to it by a very systematic piecemeal approach. We looked at each line, we wrote an expression for each line. We reasoned through each line, and then we put it all together. So when things look complex, just realize complex things break down into parts, and they're built up in parts. Don't be intimidated by it. Just work through where did this come from. Or if you have to do an analysis yourself, just say, okay, I'm going to work through step by step. What's the contribution of this? What's the contribution of this? And so on. So now we're going to go on to using this expression to determine both the best case and worst case of insertion sort. Okay, to do the best case analysis, I have now erased some of the annotations and given us a smaller version of this so we got some room to write. Let's first start with best case. What is the best possible case you can have with a sorting algorithm? Well, it actually depends on the algorithm. Believe it or not, there are algorithms that if you give them sorted data, they take a long time. But this particular one, if you give it sorted data, then every time you encounter this line here, where you're looking at a key at position J, and now you're checking starting at J minus 1. In other words, the one earlier in the array that should be smaller when it's sorted. If it's sorted, this will always fail. The inner loop will never be executed. And so remember, we wrote T sub J up here to be the number of times the outer loop is executed. That will always be 1. And we wrote T sub J minus 1 to be the number of times the inner loop is executed. And of course, that will always be 0. So all we have to do now is write out the formula that's at the top of the screen, substituting those values, and we will get the best case. So let's just do that. C1n plus C2n minus 1, no t's there, plus C4n minus 1. Plus right here is T sub J is 1, so let's sum from J to 2 to n 1. We're just counting 1, n minus 1 times. So C sub 5 times n minus 1. If you don't see that, pause and think about it. How many times do you count if that was 1? And then for this term, well, that's 0, so this drops out. And that's 0, so this whole thing drops out. And so that all that's left is C sub 8 n minus 1. Okay, maybe we should simplify this a bit here. We've got C sub 1 times n, and we've got C sub 2 times n, and C sub 4 times n, C sub 5 times n, and C sub 8 times n, all there. So we're going to start by saying this is equal to this, we'll put it in parentheses, C sub 1 plus C sub 2 plus C sub 4 plus C sub 5 plus C sub 8 n. And then we got to take care of all the leftovers, minus C2 plus, or minus C4, minus C5, and minus C8. So we're going to go minus all those, C2 plus C4 plus C5 plus C8. So that's a simplified version of the best case formula. And here is a really important point. Let's suppose we decided to call all of this A and all of this B. This formula takes the form T sub n equals A n minus B. Out of all this complicated stuff, something really simple. The time it takes is some constant. Remember, we didn't know exactly how many times it takes to do quality test and incrementing a variable as C1 and array referencing and assignment to a key as C2. We don't know what all those C's are, but we don't really need to know. They're all constants, and if you add a bunch of constants together, you just get another constant. So let's just call that A. And we don't know what all these constants are, but let's just add them together and we get constant b. So we get a much simpler version of the formula. T sub n equals an minus b. And since a and b are constant, this can only change as n changes. So as the input size gets bigger, and again, this is the best case for insertion sort, this will grow as a function of n. This is what is called a linear function because it grows with some slope and intercept depending on a and b, but as n grows, the amount of time will grow linearly. Now let's move on to looking at the worst case. I will take a second to clear the board and set this up. Okay, now we will look at the worst case. So what's the worst case? Well, the worst case would be when this while test always succeeds. So all of this stuff has to be run every time it's encountered. Notice we don't even have to describe what the data looks like. Possibly that means reverse sorted order, but you don't even have to say that to do the worst case analysis. All you have to say is that this test always succeeds so that this code is always executed. So how many times would this be executed if it always succeeds? Well, we would need to compare the key to all of the growing list of elements to the left of j. Because key started at position j, we're starting at position immediately before it, and we're stepping downwards. So this comparison would be done from position j all the way down to the end. So there's j minus 1 elements that the thing at position j is compared to. So those are j minus 1 comparisons are done, and then one additional test is done when the loop exits. So under these conditions, T sub j equals j. Comparing the j minus 1 elements for this stepping down from j down through the array, and then the jth one is for the exit. So when T sub j equals j, T sub j minus 1 of course is j minus 1, which makes sense because in our worst case we're comparing key to all of the j minus 1 elements that are to the left of the key, but we're not including in these statements here the final comparison for the exit. So these will be done j minus 1 times. If T sub j equals j, let's look at this first expression here. So that's j equal 2 to n. They're summing j equal 2 to n times. Okay, let's write that up. Now, we don't know, we don't have a formula that directly tells us what that is, but there's actually a formula that tells us if we sum up the numbers from 1 to n. So there is a formula known for the case of j equals 1 to n j. This is called an arithmetic series, and there's an equation in the back of your book that shows that this is equal to n plus 1 over 2. Okay, so we have here a formula, but our version's a little bit different. We're adding the numbers from 2 to n, not the numbers from 1 to n, but the one that we're leaving out is simply 1. So we just have to subtract 1 from this item here. So that means that this is equal to this whole thing minus 1. In other words, n plus 1 over 2 minus 1. Now we have the other case up here. We're summing j equal 2 to n T sub j minus 1. But we've just determined that T sub j is j. So we have to figure out the other case. And here I'm going to start running out of space, I think. But I'll just write over this. J equals 2 to n j minus 1. So how can we simplify this expression a bit? Well, let's just let k equals j minus 1. Sometimes when we want to simplify an expression, we can just take a more complicated thing and give it a single letter, and then we can see what we want to do here. So we can rewrite this then as k equals 1. We don't want to count too many times. We have to take 1 off of here to account for the fact that we added 1 down here. K, and that gives us a version of this formula, except wherever we see n, we're going to put n minus 1. So this turns out to be equal to n times n minus 1 over 2. We now have two usable forms for these more complicated, well, the summations. You always want to get rid of summations because they're you can't work with them algebraically until you get rid of the sigma. Okay, so now I want to write out the formula above using these, plugging in these values. I've moved the work we did down here, I've moved it up to here to give us some room to write out the final formula. So we're going to plug in the values that we just figured out. So t sub n, for the worst case, time it takes to sort with insertion sort as n gets bigger is going to be, we got c1n plus c2n minus 1 plus c4n minus 1, and now here's where it gets a little ugly, plus c5 times this expression, which we have shown to be this expression here, n plus 1 over 2 minus 1, and then we're going to have c sub 6 and c sub 7 times this term, which we simplify to this, which is equals to this in the work we just did. So let's say plus c6 times that mess up there, n minus 1 over 2 plus c7 times the same thing. Okay, and what's left here? Plus c8 n minus 1. Now, I'm not going to do all the rewriting here, but if we look carefully at this, we see that we've got some n squared terms here. There's going to be a c5 times n squared, there's going to be a c6 n squared, a c7 n squared. Actually, c5 divided by 2, and c6 divided by 2, and c7 divided by 2. So let's go ahead and write that out. c5 over 2 plus c6 over 2 plus c7 over 2 n squared plus, then there's a whole bunch of other c's times n, c1 plus c2 times n plus c4 times n plus c5 over 2 times the n that results from this n times that 1. Same thing here, c6 over 2, but here it's subtracted. And this results in a big hairy expression that you can see in the web notes. But at this point I'm going to point out that we can do the same thing we did before. Let's just call this A. And that big hairy expression, all those C's that were going to be the multiplier of n, let's just call that B. I should go back to red for this. B n. Let's make this a n squared. And then there's going to be some leftover constants. You know, there's a minus C2 and a minus C4 and so on. So let's just call that C. So what we get here, I'll darken it so you can see it better. A n squared plus b n plus c. This is a quadratic function of n. As the data gets bigger, the time it takes to sort the data grows as expressed by this function. And an important concept that we'll talk about next is that the dominating term is this n squared. Yes, this grows. These just shift it by a constant factor. This doesn't grow at all. But n squared grows a lot faster than n. So essentially, the runtime of insertion sort in the worst case is quadratic. So from a purely mathematical analysis, no implementation or testing needed, we have found that insertion sort is very quick or linear on already sorted data. Let's just write this out here. Insertion sort's time in the best case, maybe we'll just say B for best, is some function that looks like that. So the growth of that is linear in the input size. And again, purely from mathematical analysis, with no implementation or testing needed, we found out that its worst case is, maybe I'll use some other letters because it's not the same A here, r n squared plus sn plus t, say, is quadratic, because this is a quadratic equation and it grows as the rate of n squared. So a key thing to notice here is, we don't have to do implementation or testing because all those constants, they vary between different computers. Sure, the exact time is going to be different, but they all just collapsed into these constant terms. So, and constants stay constants. When the data gets bigger, they don't grow. So yeah, one computer is faster than another, but it doesn't change the growth rate. So we know that the best case is linear, and we know that the worst is quadratic, without doing any implementation or testing. But we also notice that because it doesn't matter what all those constants are, and furthermore, because the growth of these functions is dominated by these terms, yeah, that gets bigger too, but this is the one that dominates the growth rate. We can characterize the runtime of the algorithm in terms of these dominating functions. And what we're going to find out in topic 3 is that we can characterize growth rates using something we call theta. We will say, theta of n is a linear growth and theta of n squared is a quadratic growth. So this is how we're going to write the best case, and this is how we're going to write the worst case. So the good news is, because we really didn't have to worry about all those constants, they all kind of wash out, and we only had to worry about the fastest growing functions. It turns out that all that math that we just went through is not necessary. We're going to learn how to identify the most strongly growing terms for a given expression, and then we don't have to do all that math. But we do have to reason carefully to get to these expressions that I will tell you about in the next topic. Okay, that concludes the detailed analysis of insertion sort, and we have one more part to topic 2. Part D will show a divide and conquer strategy taken by a sort called merge sort, and a different approach to analysis that we need for such strategies.